This is Phil Copeman with a talk on embodied AI safety. Embodied AI safety involves what used to be called embedded systems, which is a computer that has sensors and actuators, combined with AI, artificial intelligence based on machine learning. This is not a small change involving just adding a little feature capability, but rather a profound transformation of what it means to do safety. This talk will go over why that is. To be proficient at embodied AI safety, you need to know 4 areas to the level of at least literacy. One is system safety, another is cybersecurity, a third is AI-based machine learning, and the fourth is human-computer interaction. If you're missing one of these 4 areas, expect to have trouble trying to do embodied AI safety. In this talk, we'll go on a journey to understand embodied AI safety, starting with a survey of the implications of the 4 core areas, followed by revisiting what acceptable risk means in an embodied AI system, talking about embodied AI challenges, and ending up with a reimagining of what safety engineering means when you add machine learning-based AI. The motivation for embodied AI safety is important to start with. Here's a cute little robot, and the robot's been around for a long time, but robots have had issues with some core capabilities that until now have been very difficult to pull off. The first is perception tasks. Deciding that an object is a person or something else is really hard to do, but machine learning does a pretty good job at that. Natural language interface is another capability that's really nice to have, and again, machine learning gets us most of the way there. And finally, dealing with an unstructured open world environment is an important robotic capability. All 3 of these capabilities are currently done using machine learning. But the problem is that machine learning is not something that traditional approaches to safety have been able to cope with. Now, we care about safety. I mean, here's a robot, and if it's a little toy robot, maybe it's okay. But give that robot a hammer and tell it to start beating on things because you want it to be useful, you want it to hammer nails in or something like that, gives it a way to do some potentially significant damage. So once you're interacting with the physical world and trying to make changes to that physical world, you have to think about the safety implications of taking those actions. And you start asking questions like, how safe is safe enough exactly? Nothing in this world is perfect, but it needs to be acceptably safe, whatever acceptably means. And where's the accountability for harm? If something does go wrong, where's the accountability? I can assure you that robot does not care if it gets locked up in jail for using the hammer to harm someone. So how exactly does that work? When something goes wrong, who's accountable, and how do we make sure there's an incentive to not let things go wrong in the first place? And how do we instill trust in the technology? If you have technology that has questionable accountability and can do damage, why should people trust it? How does that work? So those are all topics we'll cover in this talk. Let's dive into the 4 core areas. The first one is safety engineering. The thing about safety engineering is it's all about risk mitigation. You identify some hazards and some risks, and you mitigate them, and you make sure that the mitigation actually works. Here's a picture of someone out on a rope having some fun, and you can say, well, what's the hazard? Well, the hazard is they might lose their grip or somehow slide off the rope and fall down. And if you look closely, you can see there's a little hasp attached to a lanyard so that if this person falls off the rope, that will keep them on the rope so they don't plunge down to the bottom of the ravine. There's some technical areas with safety engineering, whether it's computers or anything else. One of the things you do is redundancy to help mitigate failures. If you look really closely at this picture, there's actually 2 ropes. So if one breaks, let's hope that the other one's strong enough to hold that person up. There's safety standards for engineering rigor. There are a bunch of safety standards associated with this equipment, making sure, for example, that the rope is manufactured and tested in a consistent way so that you know the rope is strong enough. And there's some design assurance beyond just testing. So you don't just say, well, let's see how strong the rope is by pulling on it. You make sure that there are standards for construction and quality control for all the equipment. That applies to ropes, it applies to computers. That's just how safety engineering works. There's a strong need for safety culture and independent oversight for safety. You can have all the standards you want, but if people do not take them seriously, you're not going to get safety out the other end. Let's switch to cybersecurity, the second out of the 4 core areas. Cybersecurity has to do with protecting your system from losses caused by malicious actors. The security properties vary by application. In the information technology world, in the normal everyday enterprise computing world, we tend to care about confidentiality a lot. We're worried about people stealing your password, stealing your credit card, and so on. And encryption is the typical technology used for that. But in the embodied AI world, if you have a robotaxi, while privacy does matter, everyone can see the car on the road, everyone can see you turn left, you turn right. So the confidentiality is less of an issue, and more of an issue is integrity and availability. You want to make sure that no one has modified the software to make it unsafe, and you want to make sure that the safety functions associated with mitigating risk remain available so that you don't have a loss of safety. There's an emphasis on safety, integrity, and availability rather than confidentiality. If somebody says their embodied AI system is safe because they use encryption, ask them about integrity and availability, because encryption helps with confidentiality, but not necessarily with other properties. One useful way to look at security attacks for embodied AI systems is that they're malicious faults. If you care about safety, cybersecurity attacks are a way that faults can occur that you thought probably wouldn't happen if you were just thinking about safety. For example, an attacker might introduce a fault missing from the hazard analysis, or they might violate a safety analysis assumption. You may have said a particular hazard is extremely rare, so you're not going to worry about it. Well, then the attacker's job is to find a way to make that hazard happen frequently instead of rarely, and therefore induce a safety problem into your system. A big problem with embodied AI systems in particular is that the attacker often has physical access to your system. If you have a server in a locked machine room in the middle of nowhere, it's going to be hard to get into it and modify the hardware or software physically. But if you have a car parked on the street, or you have something attached to a utility pole, it's going to be easy for an attacker to gain physical access to it and potentially modify it. So that makes security challenges a lot more difficult when you're talking about embodied AI safety. The third area to have literacy in is machine learning. Now, this talk is not going to spend an hour explaining machine learning. This is a very simplified version, but it includes the concepts that matter the most when we're talking about safety. Machine learning, in a nutshell, is you first feed a system a lot of data. We don't necessarily know how to write a particular software function by writing source code, so instead we say, well, we're just going to train it up on a bunch of data. We're going to show it a bunch of examples and let the machine learning figure out what the right behavior is. So it learns statistical properties. This is an important point. Machine learning does not learn the way a person learns. They don't learn to reason. It doesn't learn to think through. It doesn't learn to build internal physics-based models, at least with typical machine learning. Rather, it learns statistical properties. You can show machine learning a bunch of people's faces, and it does not say, oh, I know what a nose is, I know what a chin is, I know what an ear is, but rather it builds up statistical relationships that says, well, that image is statistically similar with a bunch of features to things that I've been told are a face, so it must be a face. And it generates statistically plausible results. There are different flavors of machine learning. One of them is classification. Is it a car? Is it a person? There's a family movie called Mitchells versus the Machines where the family dog, who's obviously sort of a weirdly animated dog, is it a dog? Is it a pig? And the machines all decide it's a loaf of bread as a plot device. Now, what's important here, they're not saying it's really a loaf of bread. Obviously, it's not a loaf of bread. What this classification is saying is that image is statistically more similar to a loaf of bread than to a dog or a pig. So when a machine learning system sees a human face or sees a particular person, it does not know that's a person. It doesn't know what a person is. What it's saying when it says, oh, that's a person, is that thing I'm looking at is statistically more similar to people that I've been trained on than other things I've been trained on. And that's an important difference. There's also generative art where you can take a random set of noise and you can say, well, how much catness is in there and how much Picasso-ness is in this picture? And then you can randomly perturb it and say, well, that version has a little more cat in it, a little more Picasso in it. And if you do that enough times in a row, you end up with a picture that looks kind of like a cat drawn as if it were drawn by Picasso, even though it's a completely synthetic image. Obviously, that's a simplified example, but the idea is you can generate things that statistically are similar to the thing you wanted, even though it's not an authentic image of anything in the real world. A third flavor of machine learning is large language models or foundation models, which predict the next likely output in a sequence. You can say it was a dark and stormy, and the most likely word in the English turns out to be the word night. It was a dark and stormy night, but it could be other words. And it's a little more sophisticated than that. It has tremendous ability to take context, sometimes of tens of thousands of surrounding words. And so what it produces is very sophisticated mimicry of things like language in LLMs, or things like what's the next picture in a video of a car driving down the road as seen from the driver in a vision-based foundation model. All three of these things can produce really impressive results. They're statistically very sophisticated, amazingly capable systems. But they're not artificial general intelligence. They don't actually think the way people think. And I understand this point is contested, but where I'm coming from, they don't think the way people think. They don't reason the way people reason, even though they say they're reasoning. That's not what's going on. They are statistical models. And so the important thing is, it's a mistake to attribute to them thinking. Rather, they're statistical mechanisms that can do really impressive, capable things, but don't go too far and don't assign them agency and don't assign them thinking. There's a famous test called the Turing test, in which if you're chatting with something over a typewriter keyboard and display, you can decide whether or not you think the thing on the other side is a machine or a person. And if it's a machine that convinces you it's a person, it passes the Turing test. But the thing is, we've known since a project called ELIZA back in the 1970s that some people are very susceptible to believing something's a person when it's really a machine. And it turns out that the Turing test is more of a measure of gullibility of the person on the other end of the keyboard than it is as to whether the machine has real intelligence or is just really good at faking it. The fourth core area of embodied AI safety is understanding humans and how they interact with machine learning and safety critical systems. There are two important principles here. The first is that humans have a perception response time. Humans cannot react instantly. You might think, well, they can react in a fraction of a second or a second, but it actually takes longer than that. People have to see something happen. They have to figure out what the heck am I looking at. They have to formulate a response, and then they have to initiate the response. That's perception response time. Now, some responses you can make very, very quick. People sometimes call it muscle memory. But when you have a complex situation, it can take a long time to process it. Ones of seconds, fives of seconds, tens of seconds, depending on what's going on. So that's one thing to remember. It's not instant to respond. It always takes some time to respond. The second thing is a concept called the ironies of automation. The idea is that you have automation complacency and automation bias. Automation complacency is if you're used to a computer-controlled system working really well, then it's really hard to keep paying attention. The other problem is there's a thing called automation bias, which is when presented with a human-generated output and a computer-generated output, people tend to trust the computer regardless of what's really going on. They just overtrust computers. So you add these together, people tend to get complacent and overtrust computers, especially if they've behaved well for a while. And that trust lengthens the perception response time. The more you trust it, the harder it is to react quickly when something goes wrong. So now let's have a plan where we're going to have computers that work almost all the time, but not quite all the time. And we're going to tell people that they have to intervene when something goes wrong. Well, they have limits to how fast they can do it, and it's pretty much guaranteed that the better the system is, the longer it will take them to respond because they're just not expecting it. So the irony here is that the more effective the automation is, the more ineffective human safety supervision will be. So when you hear people being shamed for checking their cell phone while a computer is driving the car down the road, I'm going to say they shouldn't do that for sure. It's the wrong thing to do. But it's basically inevitable. This is what people do. This is how people behave. And so having trouble supervising a really boring automation task is baked into human nature. You can say there's a lack of moral fiber for people who can't pay attention, but really what you're asking them to do is to be superhuman. Yes, you should put down the cell phone, absolutely. But expecting that no one will ever check their cell phone when they go hours and hours watching boring automation that almost never tries to kill them is asking a whole lot. You're not going to get safety that way. This brings about some serious ethical and legal issues. Who's responsible for embodied AI misbehavior, whether it's a car or a drone or a factory control plant or a medical device? If the embodied AI system misbehaves and there was a human who was supposed to intervene, but we know people are bad at intervening when things almost always work correctly, who exactly is responsible? Should we always blame the human, or should the manufacturer have some responsibility for building a system that is easy to supervise and does not make mistakes that are hard for people to correct for? Moreover, blaming the human for not reacting instantly is not going to make it safe. You can set up the human and say, well, it's the human's fault. Our plan is to blame the human. There's a name for that. It's called the moral crumple zone. Hey, we're going to build a system that will make mistakes, and our plan is to blame the human to protect the system. You can do that and you might succeed legally, but you're not going to be building a safe system that way, because people have a non-zero PRT that gets longer the better the automation is. So you have to have a plan for how you're going to deal with the fact that your automation will make mistakes and people will take a long time and not be perfect at catching them. What's your story for how the net combination of the computer and the person will actually be acceptably safe in the end? An overarching problem we've seen with safety is that safe enough has to include avoiding risk hotspots. A common talking point for safety for any embodied AI system is you say, well, it's safer than a human operator. And so our car driver is safer than a human driver because human drivers have these problematic behaviors. Maybe our aircraft pilot will be safer than a human pilot who makes mistakes. Maybe we'll have better outcomes than a radiologist reading medical imagery because the machine doesn't get tired and doesn't make mistakes, and so on. And so people say, well, we want to look at the net outcomes, and if the net outcomes are safer, then it's a safer system. And there's certainly an appeal to this. Now I'm going to give some very hypothetical examples, and I stress the hypothetical to make the point. If you say, well, on US roads, there are about 40,000 people killed every year, and if computer drivers were 100% of the cars and they reduced it from 40,000 to 10,000, boy, that'd be a win, because 30,000 fewer people ever dying. And there's a compelling logic to that argument. But in practice, we're probably not going to see 3-to-1, 5-to-1, 10-to-1 changes. We're going to see, at least at first, very small changes for a number of reasons. And we're also going to see there's more to it than just the numbers. You can say, sure, this computer driver is 10% safer than a human driver, but there are other types of risks that are going to be unacceptable. And so here's some examples of risks. What if there's specific unsafe behaviors? What if robotaxis keep having crashes into emergency vehicles at accident scenes and hurt emergency responders? What if they transfer risk onto the vulnerable? What if the number of fatalities cuts in half, but all of the fatalities are pedestrians? So no one inside a robotaxi ever dies, but the number of pedestrian fatalities triples or quadruples. And now what you have is lots of pedestrians dying, but the people in the robotaxis are safe. I'm going to say that will be a socially problematic situation, even though the total number of fatalities went down. What if there's harm due to embodied AI negligence? What if every single mishap that results in a death or an injury comes when the embodied AI system breaks the law? What if every single fatality involves running through a red light and hitting a pedestrian? That's not going to be okay. What if there are negative externalities? One example we saw in San Francisco was robotaxis parking in firehouse driveways so the fire trucks couldn't get out in case of an emergency. Now, no one ever pinned down a fatality or an injury due to that, but it's a problem. They can say, well, the robotaxi was just being safe. It was doing a safety shutdown. Yeah, I get that, but a human driver would be very hard pressed to justify parking in a firehouse driveway, but the robotaxis were doing that more than once. What about compensating for other mistakes? You can say, well, our embodied AI system behaved in a way that was according to the law. It wasn't negligent, but somebody else made a mistake and we failed to prevent it. You can say you didn't have a legal. A crash is a crash, and if you fail to avoid a crash, you might have a higher mishap rate, even though it's never your fault. And there's also personal and psychological safety. What if a robotaxi dumps a rider out in a really bad neighborhood at 2 a.m. instead of delivering them to their spot? There was no crash, the person wasn't harmed in a mishap, but that still could result in issues for that person. This list of things other than net safety that do matter for safety changes how you have to look at safety. And when there's a human operator present, you can say the human operator is responsible for all these kind of risks, for avoiding these risks. But once you take the human operator out, which is usually the goal of embodied AI, is to get rid of the human operator or to greatly reduce their responsibilities, someone has to take care of these higher level safety concerns. To do that, you need to do more than say we're looking at the net losses. You need to actually identify various stakeholders have risk hotspots they're in charge of. Now, let me bring that home. People think in stories, not statistics. When you saw these pictures early in this talk, did you say, oh, those pictures prove it's a safe driver? More likely, your reaction was, well, if that had been a human driver, they would have been a bad driver. So why would you not conclude the computer drivers are bad? Now, I didn't say they're bad. I asked why you would conclude they weren't bad. And the catch here is a picture of a crash is a very compelling story. And some abstract understanding of both of these companies at the time of those crashes said, oh, our cars are multiple times safer than people because we're having so many fewer crashes. But that didn't stop people from seeing these stories. Taking all this into account, I think we need to reimagine safety engineering. There's some issues that we have to address at the high level. One is societal. Net risk is not going to be enough. There's more aspects to risk than just the total mishap rate and the total fatality and harm rate. And what we're going to find out in real life is that better per human will be per incident. Every single time there's a high visibility loss event, people will judge the embodied AI system on whether they, as an operator or a reasonable operator, would have avoided that mishap. And if the answer is, oh, I would never have made that mistake, whether it's true or not, if they think it's true, that will prove to them as a person that the technology is unsafe. So selling on net risk is not enough. You're going to be judged on every single incident, and you have to have a plan for dealing with that. You're not going to be perfect, but you need to have a plan for how you plan to deal with that. The next thing is there's a technical challenge. Heavy tail edge cases, rare events with high severity. There's going to be a lot of them. So many you can't just say, well, collect the ball and it'll be fine. You're going to have to plan for incomplete training. I look at it as you have an imperfect system operating in an imperfect world, and yet it's going to happen. The next one is there needs to be an accountability approach. So here's a picture of a drone. And this drone, you might say, all right, go take a picture of this building over here. And the building happens to be on the other side of an airport. So the drone takes a shortcut over the airport and puts a flight in risk. There's an aircraft landing and there's a near collision or maybe an actual collision with an aircraft. Who's accountable for that? Is it the person that said, take a picture and thought that, of course, the drone will out-navigate around the airport because that's what it's supposed to do? Is it the programmer who told the drone to navigate? What if the drone was just trained and it's never done that before? It just decided this particular day it's going to fly over an airport. How does that work? Well, we're going to have to apply human negligence standards to AI-based systems. There's no other system that's going to be viable. We're going to have to say, well, if an AI system misbehaves, whoever had the ability to overrule the misbehavior is responsible, and probably that's the manufacturer. We also have to respect the limits of human capabilities. Humans have limits in perception response time, they have limits in automation bias and automation complacency. If the person operating that drone had photographed 100 houses on the other side of the airport, and every time it had gone around the airport, it's kind of unreasonable to expect them to monitor every second of flight this time, because they know in their heart it's going to work, but this is the time it does something dangerous. From a safety point of view, it's no longer enough to say safety is just the minimization of risk as a single metric. There needs to be a multi-constraint satisfaction approach. There are going to be a bunch of stakeholders who put constraints on how the embodied AI system is allowed to behave. Some of them will have to do with net risk outcomes, but some of them will be rules that really have nothing to do with easy to understand net risk, but rather non-interference with operations, such as not messing with aircraft flight paths, and other rules that are in place for things that are indirectly or maybe even not at all related to mishaps caused directly by this embodied AI system. Stakeholders are going to have to contribute aspects of risk constraints to the requirements, and the safety evaluation is going to have to make sure all the constraints are met rather than just saying, well, we've minimized the risks we know about, so it's good enough.